In this video we'll show how functional equation of Riemann zeta function determines where the zeros are. The Riemann zeta function is a function of a complex variable s equals sigma plus it. When real part of s is greater than 1, the function can be written as a converging summation. When real part of s is smaller than 1, the summation is diverging. Hence, the domain of definition needs to be extended through analytic continuation. Domain extension of zeta function to where real part of s is smaller than 1 can be done using the functional equation. The equation relates values of the Riemann zeta function at the points s and 1 minus s. When Riemann zeta function produces zero result, at least one of these terms is 0. 1, 2 to the power of s equals 0, hence s equals negative infinity. 2, pi to the power of s minus 1, equals 0, hence s equals negative infinity. 3, sine of pi times s over 2, times gamma of 1 minus s, equals 0. This gives us as elements of negative even numbers, i.e. trivial zeros. 4, zeta of 1 minus s equals 0. This produces non-trivial zeros. Point number 1 and number 2 are generally excluded from the consideration of Riemann's hypothesis. Otherwise, the answer would be obvious. Point number 3 gives trivial zeros, while point number 4 gives non-trivial zeros. Riemann's hypothesis is interested in the position of non-trivial zeros of zeta function, which corresponds to point number 4 in our analysis of functional equation. Zeta of 1 minus s equals 0 when zeta of s equals 0. In the case where 1 minus s equals s equals a half. But it turns out that zeta of a half is not 0. It has been established that zeta of s equals the conjugate of zeta of conjugate of s. In other words, conjugate of zeta of s equals zeta of conjugate of s. Combining this conjugate relationship with functional equation. When zeta of s equals 0, zeta of conjugate of s equals conjugate of 0, which is 0. Zeta of 1 minus s equals 0, zeta of 1 minus conjugate of s also equals 0. When 1 minus s equals conjugate of s, 1 equals s plus conjugate of s. Hence s equals a half plus I times y. It can only be satisfied when real part of s is a half. Let's visualize how functional equation and conjugate relationship will look like in the complex number plane. Here's a point s in that plane. Minus s is simply its reflection about the point of origin, which is inverse of both real part and imaginary part of s. 1 minus s is simply adding 1 to the real part of minus s. Reflecting those points on the real axis gives the points conjugate of s and 1 minus conjugate of s. Functional equation and conjugate relationship of zeta function imply that non-trivial zeros are symmetrical about the critical line as well as the real axis. Riemann's hypothesis predicts that all non-trivial zeros lie on the critical line, which is where real part of s is a half. 1 minus s equals conjugate of s can only be satisfied when the real part of s is a half. Zeta function for s with real part greater than 1 is known to be convergent and has no zero. Functional equation implies that s with real part less than 0 cannot contain non-trivial zero either. It leaves an area where the existence of non-trivial zeros of zeta function hasn't been excluded yet, which is called the critical stripe. Disproving Riemann's hypothesis requires that non-trivial zero of zeta function can exist not on critical line, although still in the critical stripe. On the other hand, proving Riemann's hypothesis means demonstrating that aforementioned requirement leads to contradiction. It has been found that there are infinitely many non-trivial zeros of zeta function, and all non-trivial zeros that has been found lie on the critical line. And they are symmetrical about the critical line as well as the real axis. Here are some of the first known non-trivial zeros. Note that these numerical values are approximations. They look random with no obvious regular pattern. This video has been long already, so our goal to find a process to extract regular patterns in Riemann zeta function, and filter out the irregularities are left for the next videos. Stay tuned.